So in this equation, I want to go over work, and we know the equation for the work done on an object is the force times the distance. So what does this equation mean, and what does this equation tell us? Well, let's say we have this block. Let's say we have this block, and let's say we apply 10 Newton force on this block. Well, if we apply 10 Newton force on this block, then we know it's going to start moving. If we apply 10 Newton force in this direction to the right, we know this block is going to start moving in this direction to the right. So let's say we applied 10 Newton force on this block for 10 meters. For an entire 10 meters where we've been applying this 10 Newton force. In this situation, how much work have we done on the block? Well, again, we know work equals force times distance. If you know the force that was done on an object, and you know the distance that that force was being done for, then you know the work that was being done on the object. So we applied a 10 Newton force. We applied a 10 Newton force for 10 meters. So if you apply 10 Newton force for 10 meters, then you use this equation to find the work done. So again, just multiplying this 10 newtons by 10 meters, we would get 100 joules. And again, Newton times meters would give you units of joules. So now we know this force did 100 joules of work on this object. However, something important to note is that whenever there's being a force being applied in the direction of motion, so we know the direction of motion was this direction. So whenever there's a force being applied in the direction of motion, then that force does positive work on the object. So we know this 10 Newton force was being done in the direction of motion. We know this block moved in this direction. So therefore we know this force did positive work on this object. So we know this force did positive work on this object. So therefore this force did positive 100 joules of work on this block. However, something important to realize is this entire time when we were applying this 10 Newton force on this object, while this object was moving, it was feeling this frictional force, this resistive force that was going in the opposite direction of motion. So while we applied this 10 Newton force, and even though this 10 Newton force was greater than the resistive force, so we had a net force in this direction, so therefore we know we had a movement in this direction, so we know the direction of motion was in this direction. But that entire 10 meters, there's this resistive force that was being done. There's this 2 Newton resistive force that was being done in the opposite direction of motion this entire 10 meters. So how much work does this 2 Newton force do? Because again, it was a force done over a distance. This entire 10 meters distance, there's this 2 Newton force done in the opposite direction. So how much work does this force do on this block? Well, again, work equals force times distance. We know this time we did a 2 Newton force. We did a 2 Newton force that entire 10 meters. So again, the distance was still 10 meters. So in this situation, to find the work that this force did, again, we just use this equation. And solving this, 2 times 10, we would get 20 joules. So now we know this guy did 20 joules of work. However, the convention is, and just something you need to memorize, is when there's a force being done in the opposite direction of motion, whenever there's a force being done in the opposite direction of motion, because again, we know the motion was in this direction. However, if there's a force being done 180 degrees in the opposite direction of motion, that force does negative work on the object. So we know this 2 Newton force did negative work on this object. So therefore, this 2 Newton force did negative 20 joules of work. So this 10 Newton force did positive 100 joules of work, while this 2 Newton force did negative 20 joules of work on this object. Because again, whenever there's a force in the direction of motion, that force does positive work. When there's a force in the opposite direction of motion, 180 degrees in the opposite direction of motion, that force does negative work. So now we know this force did negative 20 joules of work, while this force did positive 120 joules of work. So we know in total, these two forces in total did positive 80 joules of work. In total, there was positive 80 joules of work done on this object. And another way you could have solved this was just find the net force that was done. Because again, we know work equals force times distance. However, we could have just found the net force. And if we had a 10 Newton force in this direction and a 2 Newton force in this direction, we know we had a net force of 8 newtons. So then you could also use this equation plugging in the net force. And we know the net force was 8 newtons. And again, we know the distance was 10 meters. So this would give us positive 80 joules of work, which again, when you plug in the net force, you find the net work that was done. You know the net force that was done over this distance, so you can find the net work that was done. So this would give us 80 joules, which we already said. We already said by finding these two, the net work, the total work, adding these two was positive 80 joules of work. So again, these are just things you need to be familiar with. If there's a force in the direction of motion, that's positive work. If there's a force in the opposite direction of motion, that's negative work being done. So now that we know this, the truth is that in reality, it's actually a little more complicated than that. So let's say we did a force in this direction of 10 newtons. Then again, we know if we do a force in this direction of 10 newtons, we know this force has a component of this force in this upward direction, and it has a component in this x direction. We know this force is made up of components, an x component and a y component. And these two components add up, creating this net force of 10 newtons. So if we have a 10 newton force in this direction, let's say this is 60 degrees. 60 degrees from the horizontal, then we know this 10 newton force has a component of this force in this x direction. So we know this has a component of the force in the x direction. So therefore, there's a component of this force in the x direction. So assuming that force overcomes the frictional force, we know that force is going to cause movement. So now if we apply this 10 newton force in this direction, it has an x component, so it's going to cause some movement. So let's say we have 10 meters of movement. So let's say, again, we applied 10 newton force in this direction, and we apply that 10 newton force in this direction for 10 meters. Well, we're applying this 10 newton force and it moves, and we keep applying this 10 newton force in this direction for an entire 10 meters. How much work has this 10 newton force done on this object? Well, again, we've already learned the equation. We've already learned work equals force times distance. However, in reality, this is a bit of a simplification, and another form of this equation is that work done equals force times distance times cosine theta. So what's the differences with these two equations? Well, again, when using this simplified form of the equation, what you're doing is you're finding the force that was done in the direction of motion. You find the component of this force that was done in the direction of motion, and it's that force that you plug into this equation. So if we were to use a little bit of trigonometry, we know cosine theta equals adjacent over hypotenuse, so therefore hypotenuse cosine theta equals adjacent. So representing this force as a triangle, we know this would represent the hypotenuse and this would represent the adjacent. So now we know the hypotenuse and the cosine, so we could plug these in to find the adjacent. And we would see the adjacent, using this trigonometry, we would see this adjacent would be 5. This would give us 5. Plugging in 10 and 60, we would get a of 5. So this would be 5 newtons. So this tells us if we have a 10 Newton force in this particular direction, 60 degrees from the horizontal, then we know this 10 Newton force has a component in this x direction, and it's 5 Newton force that's causing that movement. So it's this component of this force that we plug in to find the work done. So again, we would plug in this force of 5 newtons, and again, we know the distance is 10 meters. So now we would get the work that was done. The work that was done was positive 50 joules of work, because we know this force was done in the direction of motion. So now we know this 10 Newton force essentially did positive 50 joules of work, because this 10 Newton force, all we were interested in was the component of the force in the direction of motion. This was all we were interested in. So it's that force that you plug in to find the positive work that was done. So this force did positive 50 joules of work on this object. However, what's this equation then? What's going on with this equation? Well, when using this equation, instead of finding the component of the force in the direction of motion, this equation, even though it looks a little more intimidating and a little more complex, it actually is a little easier and it does some of the work for you. For this equation, you would just plug in this original 10 Newton force. You would just plug in this original 10 Newton force. However, and then you find the distance traveled, and then you would find the theta between the direction of motion and the direction of force. So that's what this theta is. When using this equation, this theta is the angle between the direction of motion and the direction of force. So you would plug in that 60 degrees theta, and you would plug in the original force, and that would give you the positive work that was done. So again, you would plug in 10 newtons, the original force, the distance was 10 meters, and then cosine 60. That's the theta, the angle between the direction of motion and the force. So again, this would be 60. And if you were to plug this in the calculator, it would give you positive 50 joules of work. So this is a different way you can find the work that was done. But again, the point is if we apply a 10 Newton force in this direction for 10 meters, we're doing positive 50 joules of work on this object. And there are these two different ways. One is you could find the component of the force in the motion. You could find the component of the force in the direction of motion and plug in that force and find the work done. Or you could be lazy and just plug in the original force. Plug in the original force of 10 newtons, so plug in this force instead of the direction in the motion. You plug in the original force, and now you just plug in the cosine theta, the theta between the force and the direction of motion. And then now this equation does some of the work for you. And then it would again give you the same positive 50 joules. So this cosine theta keeps into account this force, the direction, and the direction of motion. It keeps that into account, and it kind of does the work for you. And again, just plugging in that original force, it does the work for you, and it finds the component in the direction of motion. But again, the point is, these are two equations that they tell you the positive work that was done. Again and again, so this one looks a little more intimidating, but really does some of the work for you. For this equation, you would plug in this 10 Newton force. For this equation, you would plug in the component of the force in the direction of motion. And sometimes I actually prefer this equation. I prefer this equation. For example, let's say we had a little more complicating situation. Let's say simultaneously there was a bird pulling on a string in this direction of 4 newtons. So, and again, let's say this again was 60 degrees from the horizontal. What was the net work that was done on this block? Well, again, we can find the positive work that was done by this 10 Newton force because we know this 10 Newton force had some component of this force in the direction of motion. It had some component of the force in the direction of motion, so therefore this was positive work that was done. However, we know this has a component of the force in the opposite direction of motion. This 10 Newton force has a component of this force in the opposite direction of motion. And if with some trigonometry, we would see that this component of the force would be 2 newtons. This 10 Newton force in this direction would have a component of this force in 2 newtons in the opposite direction of motion. And again, we know this is the opposite direction of motion because again, we know in total, we know the net forces would allow this object to move in this direction. So we know this is the direction of motion. So therefore, this is positive work that was done on the object, while this is negative work that was done on the object. So how much negative work was done? This 4 Newton force, how much negative work did it do? Well, again, you can simply just use this equation. The work that was done equals the force times distance times cosine theta, where this theta is the angle between the direction of motion and the directed force. So again, we know when using this equation, we can be lazy. We can just plug in the original force of 4 newtons. The distance was again for 10 meters. That 10 Newton force was done for 10 meters. And again, cosine theta. But what is this theta? Again, it's the angle between the direction of motion and the force, and this applied force. And again, we would see that again, this would be 90 degrees. And again, if this is also 90 degrees and this is 60 degrees, we know this is 30 degrees. This is 30 degrees and this is 90 degrees. So the angle between the direction of motion and the directed force is 90 plus 30 is 120 degrees. So therefore, this theta is 120 degrees. So now plugging this into the calculator, we would get negative 20 joules. So we know this force did negative 20 joules of work on this object. And we know that makes sense because we know this had a component of the force in the opposite direction of motion. So we know this should give us a negative work. And again, the point is this equation does some of the work for you. Instead of having to find the component of this force in the opposite direction of motion and then plugging in that force and then finding the distance, instead we can just be lazy. We can just find the original force and just find the angle between the force and the motion and just plug in that theta in that original force. And then this cosine 20 it would spit out a negative value and it would do the work for you, spitting out a negative 20 joules of work. So you know this did negative work. And again, whenever you have a theta that's greater than 90 degrees, you know then it's the force is in the opposite direction of motion. So because this theta was greater than 90 degrees, it gave you a negative work. So this is a bit of this does some of the work for you. This no pun intended, but this makes it simple, and this does the work for you, and you can just plug in. So again, this equation looks intimidating, but it's actually a little easier. So now we know this force this 10 Newton force did positive 50 joules of work, while this 4 Newton force did negative 20 joules of work. So we know in total these forces in total did positive 30 joules of work. And again, there are different ways we could have come to that conclusion. Again, we could have found the net work that was done in the direction of motion. Because again, we know this guy had 5, positive 5. This guy had 2 in the opposite direction. So we know in total there was 3 newtons that was done in the direction of motion. Work equals force times distance. So again, we know in total there was 3 newtons done in the direction of motion. It was done for 10 meters. So this would give you 30 joules. Positive 30 joules of work, which again we solved. So again, the point is there are different forms of this equation that you can use. You can use this form of the equation, or work equals force times distance. There are these two forms of the equation. These two forms of the equation. And again, depending on which one you're more comfortable, you can use, but this one, you need to find the component of the force in the direction of motion. You have to do that extra work, where this equation, you just plug in the original force, and it does the work for you. It finds the component in the direction of motion for you.